Swayam Prabha. Digital India. Educated India.
I hope you are well rested after a crash course in linear algebra. If things are still hazy and fuzzy, don't worry, I have a cheat sheet at the end of this class where if you look at it, everything else will be clear in terms of conditions of when the solutions exist and so on. Towards the end of yesterday, we looked at unconstrained optimization, and which is where we'll just go have a very quick recap. So remember, we are trying to minimize a function f of x, where f is from Rn. It takes a vector of size n and returns me a real number. I'm trying to find the minimum of this function. If you recall, the first order necessary condition is that the gradient should be equal to 0. Remember, the gradient is a n-dimensional vector. And the second order necessary condition is that the Hessian is positive semi-definite. The Hessian, if you recall, is a matrix of mixed partial derivatives. Along the diagonal, it is the second order partial derivative. The off diagonal elements are the elements of the mixed partial derivatives. So Hessian is positive semi-definite is equivalent to saying all the eigenvalues are greater than or equal to 0. So these are the necessary conditions of optimality. Just because they are satisfied does not mean that you have a minimum. It is possible. I can construct certain examples where the gradient is equal to 0. The Hessian is positive semi-definite. However, it is not a minimum. You can have things like saddle points. What happens is, along certain directions, the function increases if you go, but along certain other directions, if you go, the function decreases. So it behaves in a very weird manner, and you could have saddle points. However, if the Hessian is positive definite, that means all the eigenvalues are strictly greater than 0, then you are assured that you are at least at a local minimum. I cannot make any guarantees about global minimum, but at least you are at a local minimum. Most theories and algorithms are unconstrained or optimization can only guarantee convergence up to local optimum. There is no guarantee, very few, unless the function itself has certain special properties, such as if you are working with convex functions. For a convex function, any local minimum is a global minimum. So if you remember how convex functions are defined, I will not, so I'll just briefly define this. So if you give me 2 points x and y, and then you look at the line segment joining the 2 points x and y, that can be described as lambda x plus 1 minus lambda times y, where lambda goes from 1 to 0. So if lambda equal to 0, you get y. If lambda equal to 1, you get x. So as you vary lambda between 0 and 1, you are basically going along this line segment joining these 2 points. What convex functions is, a function is convex, what it says is that if this condition is satisfied, then the function is convex. Now, certain functions, if the function is convex, there is one good news I can give you. If you converge to an optimum, it is automatically a global optimum. So that's why there's two good pieces of information. First is theoretically, if you converge to an optimum, it is global optimum. Secondly, there are algorithms which have been built around convex optimization problems, and several problems involving machine learning can also be posed as convex optimization problems. And so there are specialized algorithms which work for certain classes of convex optimization problems, and therefore the advantage is that when you are guaranteed to reach a minimum, you are also guaranteed to reach a global optimum, and these algorithms have been tailored for certain classes of convex functions. So just to recall and recap, the first order necessary condition is that the gradient is equal to 0. The second order necessary condition is that the Hessian is positive semi-definite. A sufficiency condition is that the Hessian is positive definite. Which means all the eigenvalues are strictly greater than 0. Then you are automatically guaranteed that it is a local minimum. For a convex function, any local minimum is a global minimum. What happens when, so what I'll do now is, I'll quickly go over how do you compute gradients, and I'll give you formulae for gradients and Hessians of some commonly used functions, and these will be very useful. when you in later in case of applications. Right? So let's say the function f of x is a constant. F is just a constant, right? The gradient would be, remember the gradient is an n by 1 vector, Hessian is an n cross n symmetric matrix. So the function is a constant, the gradient as we expect should be equal to 0, the Hessian is also a 0 matrix. When I say 0 over here, this is a 0 matrix n by n, and when I say 0 over here, it is a 0 vector of n cross 1. Now, if a function is linear, C transpose x, right, because it's linear in this case, or f is equal to C1 x1 plus C2 x2 all the way up till Cn xn. The function is linear. The gradient would be an n-dimensional vector. It's just this vector C. Remember, C is an n-dimensional vector containing C1, C2, Cn, and it's a column vector. The gradient is just that vector itself if the function is linear. As you can imagine, the Hessian is also a 0 over here. It's a 0 matrix of size n cross n. Now the function is quadratic. Now quadratic functions you can represent as, there is a reason why I'll put a half over here. X is of course n cross 1, h is n cross n, and I'm going to choose it as symmetric. I'm going to choose h as symmetric. If h is not symmetric, I can always make it a symmetric form. So I'm just going to work with a symmetric matrix over here. Now the gradient, if you want to think about this as functions of one variable, if you have a quadratic function half hx square, the gradient would be hx, the derivative would be hx. So generalize, you can prove this analytically by taking derivatives. Now the gradient would be hx over here. You need, the order is important, you cannot have xh or and so on, because you need to get a vector over here. And the Hessian is just the matrix H. Now, what about an arbitrary function with maybe a constant term, a linear term, and quadratic term? So f of x is equal to the gradient is going to be hx plus c. You can verify that this is an n cross 1 vector. The whole thing, gradient is an n cross 1 vector. The Hessian is just going to be the matrix H over here. So now if you give me a purely a quadratic function which involves a linear term, a quadratic, I am deliberately not including the constant term because it will not contribute anything to either the gradient or the Hessian. So if you give me a function of this form, if you ask me whether it is a minimum, whether it has a minimum, you need to solve for hx. So for an optimum, of course we know that gradient is equal to 0. So function is purely linear. It does neither has a minimum nor a maximum unless the c vector is identically 0. As you can imagine, a linear function there are directions along which it keeps on increasing, there are directions along which it keeps on decreasing. Therefore, a purely linear function, unless it is identically 0, it will not have either a minimum or a maximum. For a function of if a function has to have a minimum or a maximum, it should have at least a quadratic term. So therefore, it has to have either c transpose x plus x transpose hx. So if you want to solve for the minimum of such a function, the gradient equal to 0, you need to solve for hx plus c equal to 0. And if you want to guarantee that it is a minimum, h has to be either positive definite or positive semi-definite. And here you can go back to whether solution exists or not. If there is a unique solution, many solutions, all goes back to the theory of linear equations that we studied yesterday. So this is of course only for a gradient equal to 0 is true for arbitrary functions. Hx plus c equal to 0 is true when the function is as a linear term c transpose hx, c transpose x plus a quadratic term half x transpose hx. Usually now it will be clear why we deliberately introduced the half term over here. The reason is in the gradient the half factor is not coming. If there were no half over here, in the gradient the factor 2 would keep coming. And since we do a lot of work with gradients and with Hessians, we don't want to have these factor 2 coming up unnecessarily subsequently. In order to avoid that, we solve that problem by putting a half right at the front, at the start in my objective function itself, or in my quadratic function itself, I will put that factor half, so that when I take derivatives and Hessians, the factor 2 does not, or there is no factor of 2 or whatever coming up later. That is it's only a purely aesthetic reason why it is conventional to put a half in the quadratic term in the function over here. So now for non-quadratic functions, you need to use some numerical technique to solve for the minimum. In the interest of time, we will not be working on methods for solving these, except that I will just give you an intuition. You have to use an iterative or a numerical technique to go along these. A standard technique would be, remember, at any point the gradient or the negative gradient is the direction of maximum decrease. So you can do a search, that is, you can go along the minus gradient up to a certain point and then keep iterating over and over again. And this kind of an algorithm you will see later on when you do neural networks, because back propagation or gradient descent is a very standard way of solving. It comes up when you solve neural network problems. That the idea is negative gradient is the direction of steepest maximum decrease. So you go along that direction because you want to decrease the value of the objective function. You go along that direction up to a certain point and then recompute the gradient at that point and go along the negative gradient, and you keep iterating this. Let me start with a very simple geometric problem. So let me start with, this line is x plus y equal to 1, and I want to minimize a constraint problem. Means there are constraints which I have to respect. In the earlier case when we did unconstrained optimization, x was my decision variable. It was allowed to take any arbitrary value that I am allowed to, as far as they and so on. Whereas in constraint optimization, there are certain constraints which I have to respect. For instance, I am asking you to minimize this function x minus 3 the whole square plus y minus 3 the whole square, such that, or subject to x plus y equal to 1. What does this mean? This means I have to be on this line, and subject to me being on this line, I want to find the minimum of this function. Now in this case, I can also give you a geometric interpretation. What this means is, this is the point, roughly the point 3, 3. I am asking you to find a point on this line which is at the shortest distance from 3, 3. That is a geometric interpretation of this problem. I want to find the shortest distance of this line from this point. And we know geometrically when that happens, when you drop a perpendicular from that point to this line. That's why the geometric condition happens. That when you drop a perpendicular from this point to this line, the point of intersection of that perpendicular to that line happens to be the shortest point, closest point to this line. Now we will treat this as an optimization problem. We know in this case, using pure geometry and some coordinate geometry, we can solve it. I am going to now give you an interpretation in terms of optimization problems, in terms of gradients and so on. Right. Unlike the case in unconstrained optimization, I have to be on this line. I cannot go out of this line. When I am trying to solve this problem, I have to respect the constraint that I have to be on this line. So if you give me a point, I cannot claim that this is an optimum at all. This is not even a feasible point because it doesn't even lie on this line. So the only thing which I have to do is, I have to look at points which are on this line and then ask the question, is it a minimum? Recall, how did we decide whether a point is a minimum necessary condition for optimality in unconstrained optimization? If you gave me a point and the gradient were not 0, what did I say? It cannot be an optimum because I can go along negative gradient and the objective function value will decrease. So I will use similar ideas over here. Let me claim that this point is an optimum point. And then I will come up with a reason why it cannot be an optimum. We know this is not an optimum point because that perpendicularity condition has to be satisfied, and here clearly it is not satisfied. Now why cannot this be an optimum point? Now at this point, remember, I can draw, now I have to be on this surface. And at this point, if I drew an objective, for this point, the objective function f is of course, x minus 3 the whole square plus y minus 3 the whole square. At any point, I know the gradient points in the direction of maximum decrease, and negative gradient points in the direction of maximum decrease. So at this point, as far as the objective function is concerned, in which direction would the gradient or the negative gradient point? It will point radially. Remember, when you have a circular function over here, the gradient is perpendicular to the tangent, and the gradient points in the direction of maximum increase. So if the objective functions have circular shapes, the gradient and the tangent are perpendicular to each other. Maybe if I missed this, let me repeat this. The gradient and the tangent plane are perpendicular to each other at any point. Therefore, at this point, the gradient is perpendicular to tangent. For the functions of this kind, the negative gradient, they point in the radial direction. Negative gradient will point towards the center, the gradient will point away from the center. So for this point over here, I claim it cannot be a minimum. Why? Because minus grad f is pointing in this direction. Minus grad f is pointing in this direction. What does that mean? I cannot be a minimum. Remember, if I am at this point, I cannot go in any arbitrary direction. If I have to be at this point, the only way I can check about the conditions of optimality is I have to make a small change from that point and then ask whether the function value is increasing or decreasing. Now if I am at this point, I cannot go in very arbitrary directions. There are only certain directions in which I can go. In fact, pretty much I have to be on, if I am at this point, I cannot go into this, these directions are not allowed. These are all unallowed directions because I am going away from the line. So I can only go along certain directions which are, I can go only along certain directions. And what directions are those? Those directions which keep me on the line. So likewise, what could be an example of such a direction? This is an example of such a direction. This is an example of such a direction. These two directions keep me on the line. Basically the same direction. One is 180 degrees the other way. So only I can go along these directions. Now what happens if I go along these directions? So I am trying to find the shortest distance of this point from the line over here, and my claim is this could not be a minimum. At this point, my minus grad f is pointing in this direction. I cannot go, these directions are unallowed or disallowed directions, so let me wipe them out. So I can go along pretty much only one direction, and that direction is which keeps me along this line. So I can go only along any of these two directions. Now if minus grad f is pointing in this direction and it is non-zero, we know at this point gradient is not 0 because the gradient is 0 only at this point over here, but this is not a feasible point, so this is not, I cannot accept this as my optimal point. Any point that has to be optimal has to be on this line, it has to be a feasible point first. At this point, the negative gradient is pointing radially towards the center of the circle over here. Now I can go along this direction or this direction. Now what happens if I go along this direction? What can you say happens to the value of the function? The value of the function will decrease. Why? Because you take minus gradient, I can resolve it, I can find the component of minus gradient along this direction over here. It has a non-zero component. So which means if I take minus grad f and take a component along this direction, if I go a very small amount along this direction, the function value only has to decrease. Like if I take a value, if I take minus grad f and take a component along this direction, the function value only decrease. Therefore, this could not have been an optimum point. Likewise, let's take this point, some other point, and ask whether this could have been an optimal point. So here minus grad f is again pointing along this direction. At this point I can go here or here. If I take minus grad f and try to get the component along this direction, I get a non-zero component. So which means if I go along this direction, function value decreases. If I go along this direction, f decreases. If I go along this direction that I am pointing, f decreases. So the function value, neither of these 2 points could be an optimal point. Now let's take the point over here which is perpendicular. We know upfront from intuition and from our high school geometry that this is the optimal point which has the which is closest to the point 3, 3 over here. When you drop a perpendicular, the point of intersection of this perpendicular with this line is my optimal point over here. Now at this point what happens? minus grad f is pointing along the perpendicular direction. Minus grad f is pointing radially towards the center of this circle. Now, at this point there are two directions in which I can go. Let me draw it over here just to be clear. This is minus grad f, this is where it is perpendicular. Minus grad f is pointing towards the center of the circle, it is perpendicular over here. At this point I can go in this direction or in this direction. Now, does minus grad f have a component along any of these two directions? No, because these two directions are perpendicular. If you go north, you can never go east. If you go north, by turning 180 degrees, you can go south, but you can never go east or west. Right? So if you go along this direction over here, if you have minus grad f is perpendicular, it has no component along the other direction, perpendicular direction over here. So at this point, at least locally, if you ask me what is happening when I make a small change, I will come to the conclusion that f neither increases, that is, I reached a stationary point. At any of the other points where it is not perpendicular, minus grad f will have a component along a feasible direction, and if you go along that direction a small amount, you will continue to remain on the constraint and the function value will only decrease. Therefore, neither of these could have been an optimal point. So the point where it is perpendicular, where you drop a perpendicular to this line, that happens to be an optimal point, and minus grad f is perpendicular to the constraint surface. So what do we know? I have drawn only one constraint over here, because in 2 dimensions it makes sense only to draw one line or one constraint, because there is no point in drawing several constraints. We will come to that later. For higher dimensions, what I will do is I will take the easy way out and just generalize this and ask you to take it with a leap of faith. I will write down the conditions when there are many more functions, many more constraints, and there are high dimensions. But right now we will understand what is going on geometrically in 2 dimensions. So at an optimal point, minus grad f is perpendicular to the constraint line. Right. Now, what is this constraint line? This is x plus y minus 1 equal to 0. Now, for this line, at any point, if I can, let me call this, for this line at any point, I can draw a normal vector. Right. So, what does this mean? If minus grad f is perpendicular to the constraint line, minus grad f is parallel to the normal vector. Or let me say, now you might wonder why I am going in a convoluted manner. The reason will become clear so that I can write down the conditions of optimality. Minus grad f is perpendicular to the constraint line. Now what else is perpendicular to the constraint line? For a line at any point I can draw a normal vector. At any point for a line over here, at any point I can draw a normal line vector over here, because so at this point, if minus grad f is perpendicular to the constraint line, it is therefore parallel to the vector which is perpendicular to the line. Now you might think this is very convoluted, but the reason is how do I characterize this condition of perpendicular to the constraint line? I will be able to characterize in terms of the normal to the constraint line. So minus grad f is parallel to the vector that is perpendicular to the line. Now what is a vector that is perpendicular to the line? How do you find the vector which is perpendicular to the line? In this case, let me take this, let me call this as h equal to x plus y minus 1. Now think about this, forget about f, the objective function, for a moment. Just think about this as the function h equal to 0. Think about this as h equal to 0. So at any point, what does the gradient pointing in? The gradient is pointing direction of maximum increase. It is also perpendicular to that line, to that surface. So the gradient at any point over here, grad h is equal to 1 comma 1. Right? You look at the derivative, how it is defined, h equal to x plus y minus 1. Grad h is the vector 1 comma 1. Now grad h is perpendicular to the line. I know minus grad f is perpendicular to the constraint line, grad h is perpendicular to the constraint line. So what can you say about minus grad h and grad f? grad h is perpendicular to the line. Minus grad f is perpendicular to the constraint, grad h is perpendicular to the constraint line. Therefore, what can you say about minus grad f and grad h? They are collinear. So, what can you say about that? But lambda is, remember, lambda is some unknown scalar that we still have to determine. So, unlike in unconstrained optimization, the gradient cannot be set equal to 0. What we have done is, we have set the negative of the gradient equal to some scalar multiple of the gradient of the constraint. So, now you will appreciate why I went in a convoluted manner and said minus grad f is perpendicular to the line, minus grad f is parallel to the vector that is perpendicular to the line, because I know what vector is perpendicular to the constraint line, grad h. Grad h is perpendicular to the constraint line, therefore minus grad f is a scalar multiple of grad h. Now you might ask this question, what is the value of lambda? How do I get the value of lambda?